Hello, this is section 7.12. And our subject for today is substitution and elimination with other substrates or functional groups. We're going to talk first about a very special functional group in organic chemistry called the organic sulfonate. And organic sulfonates are characterized by having some alkyl or other group attached to this SO3 functional group. And the SO3 functional group is very stable due to the fact there's a lot of resonance stabilization that comes from having all these oxygens here. As you can see, oxygen electron density can flow down and then back up into another one and up to the top one if it wants, and so on. And there are three main types of organic sulfonates that we use in organic chemistry. They have their own abbreviations and very different structures. So MSOH is called methane sulfonic acid, so named because there's a methyl group in the sulfonic acid. There's a para-toluene sulfonic acid. You'll learn more about the name para-toluene in Organic 2, but for right now, in Organic 1, this is all that you need to know. And also trifluoromethane sulfonic acid, because there's a trifluoromethyl group there, and that has the abbreviation TFOH. We call this one triflic acid, this one tosylic acid, and this one mesic acid. Don't ask me why, it just is the convention in organic chemistry. What makes them also very special is that they are very strong acids, as strong almost as strong acids like HCl, HBr, and HI. In fact, triflic acid, trifluoromethane sulfonic acid, is stronger than HI. And because these are such strong acids, they are very good leaving groups, which makes them very useful for substitution and elimination reactions. So the question becomes, how do we put these groups onto molecules? And it's fairly straightforward. You can, for instance, take an alcohol, treat it with tosyl chloride and pyridine, and get the tosylated alcohol. And we say tosylated because, again, in organic chemistry, every time we have performed an action on something, we tend to use the ated suffix. So it was tosylated, meaning that the tosyl group was put onto the molecule. And this reaction is a good one for you to learn because it is very similar to a lot of reactions we will do with alcohol groups, which you'll learn about in a second. The mechanism for this is some alcohol, even a chiral one like this, attacks the tosyl chloride molecule. And when it attacks the tosyl chloride, it kicks out the chlorine atom that was attached to sulfur, leaving us with the tosylated alcohol that is also an oxonium. The positively charged alcohol is then relieved of that extra proton via pyridine, this guy here that we have seen a few times. He's a good base, and he can deprotonate this molecule to give us our final product, this tosylated alcohol, plus the protonated pyridine and the chlorine that we kicked out. And these organic sulfonates tend to favor substitution reactions if the substrate is primary, this one's secondary. But if the substrate is tertiary or secondary, they tend to favor elimination. So keep that in mind whenever we're looking at specific reactions, because if you have a tosyl group, a mesyl group, or a triflic group, then perhaps they can be eliminated or substituted depending on the type of substrate that they're on. All right, now let's talk about alcohols. This is not the type of alcohol that we all like, but this is a general term for an alcohol group attached to an alkyl group. And what makes alcohol special is that the OH by itself is a bad leaving group. But if you protonate the OH to give you this OH2 oxonium ion, then it's a good leaving group, and you can start doing some of these substitution and elimination reactions there. For instance, let's say that you wanted to do this reaction. Here, you took this alcohol and H2O. This should actually be HBr. There we are. You have this alcohol and you heat it up in HBr. What you will get is substitution of the alcohol group with the bromide. And how that happens is because in the first step, you protonate the alcohol group with HBr. And this happens because the pKa of HBr is so incredibly low that it will protonate this alcohol group. Once you make the oxonium ion, the bromine that's left over from that reaction then can perform an SN2 reaction and kick out the water, leaving you with the alkyl halide and water molecule. The other interesting thing about alcohols is if you perform the same protonation, but you don't have a nucleophilic anion around, it does something else completely. In fact, that is shown here when you do the reaction in concentrated sulfuric acid. When you do the reaction in concentrated sulfuric acid, you get an alkene product and water instead. We call this a dehydration in both cases because you lose water in the process, and hence dehydration. So the mechanism is fairly straightforward. You have, again, the first step being protonation of the alcohol with sulfuric acid, leaving you the protonated alcohol and the bisulfate anion. Then, once you have that, the H2O hydronium ion leaves, leaving you with a carbocation on this tertiary carbon and the water that you dehydrated from the molecule. That water can then act as a base, take a proton, and give you the alkyl product, the hydronium ion, and the HSO4 minus anion. That was section 7.12.